In this video, we're going to talk about integration by parts. This is a technique that is particularly helpful for integrands that involve or that contain different types of functions. Okay, kasi we have algebraic functions or expressions, and we have the transcendental functions or expressions, di ba? So if you have a product of two different types of functions, then it's not readily integrable in its initial form. So you have to do something first, and this is the applicable technique, integration by parts. Okay, so again, algebraic and transcendentals. Under the transcendental functions, we have trigonometric, inverse trigonometric functions. We also have exponential and logarithmic functions, and hyperbolic and inverse hyperbolic. The last two functions are not included in our discussion, talking about hyperbolic and inverse hyperbolic. Okay, so again, integration by parts, it's not limited to product of different types of functions. It can still be applied for algebraic expressions lang, pero its application is perfect for product of two or more different types of functions, no? For example, product of algebraic and exponential functions or expressions, like this integral in general. So x raised to n is a constant, times e raised to ax, where a is also a constant, dx. So algebraic na portion is itong x raised to n, right? And then exponential, of course, is e raised to ax. Okay? Or algebraic and trigonometric, like this one. Then algebraic and inverse trigonometric, or algebraic and logarithmic, or exponential and trigonometric. Okay, so these are just some of the examples where we can, where IBP can be perfectly applied. Okay, so again, it's not limited. The application of IBP, or integration by parts, is not limited to these types of integrals lang. Okay, pero its application works perfectly for these types. Okay, so we'll focus on them. Now, working equation for integration by parts. We have a working equation. It's a simple na equation. Is this one. Okay, integral of u dv is equal to or equals uv minus the integral of v du. Okay, so again, u and v here are placeholders for any expression or any other variable. Okay, so let's talk about this working equation. This is derived from or obtained from the product rule of differentiation. Okay, so suppose we have a function y equals, so what I'm trying to do here, class, is to derive this working equation for integration by parts. Okay, so let's start with a function y equals, so that would be two different functions, no, u and v, so that we can apply product rule. Okay, so let's take its differential. That would be dy equals u times the differential of v plus v times the differential of u. Right? Now, let's take its reverse operation. So what we did was we took the differential. Now let's take its reverse operation. So we integrate both sides of the equation. Okay, so integrating both sides, we have integral of dy on the left hand side, and then integral of u dv plus integral of v du, right? On the left hand side of the equation, integral of dy, this will just be equal to y, right? Then let's leave the right hand side of the equation as is for now. So integral of u dv plus integral of v du. Alright, and then initially we established that y is equal to what? Y is equal to the product of u and v. So we can plug in uv for y, right? So u times v equals the integral of u dv plus integral of v du. Okay, and then from here we can either isolate integral of u dv or isolate integral of v du. Pero by practice, we usually just isolate itong first term, itong integral of u dv. Okay? So integral of u dv, isolate lang on one side of the equation. Equals, so transpose itong integral of v du. So maging negative integral of v du siya. So uv minus itong integral of v du. Right? This is now the working equation for integration by parts. Right? So integral of u dv, integral of u dv equals uv minus v du. So how do we apply integration by parts? So as the name suggests, no, by parts, we have to break the given integral into two parts. One will be utilized as u, and then the remaining expression will be for dv. Okay, that's why it's called integration by parts. So two parts. One portion of the integrand is u. The other portion of the integral will be for dv. Okay, and then we apply different processes. Ang u should be differentiated. Okay, kumbaga it should undergo the differentiation process. While ang dv naman na portion ng integrand should be integrated. Okay, meaning it should undergo the integration process. Okay, and then the result is this expression on the right hand side of the equation, uv minus integral of v du. So kumbaga, after the integration process, there will be another integral na ma-generate. Pero usually naman, the new integral na ma-generate is easily integrable naman. So let's look at an example to further understand IBP. Okay, let's take for instance integral of x times e raised to x dx. So what we have here is a product of an algebraic expression, which is itong x na portion, and exponential expression, e raised to x dx. Okay. So to carry out integration by parts, remember we have to break the given integral into two parts. Okay. So one portion will be used as u, and then the remaining expression will be the dv portion. Okay. So we actually have a few ways to carry out integration by parts, or a few ways to break the integral into two parts, no? Pero only one way is the correct way. Okay, so isa lang. So for example, we have 4 ways here, no? Let's focus on the first one, itong sa pinaka left hand side. So we can use, o kumbaga we can specify u in this case as x, and then the remaining expression e raised to x dx is the dv portion. Or the product of x times e raised to x is the u portion, and then the remaining portion is, and the remaining expression is dv. So far class, when we break the integral into two parts, ang dv na portion should always contain the differential na term. Okay. kasi ang dv na portion should be integrated, di ba? Ang u na portion, no problem, kasi it will just be differentiated. But again, dv should always contain dx or d of any or differential of any variable na given. Okay, pero in this case we have x, so dx should always contain dx. Okay, and then third one here, e raised to x ang u, and then x dx ang dv. Okay, or i-group together lahat, x e raised to x and dx as dv. Tapos we have a factor of 1, diba? It's an identity property. Identity property. So we can specify that we have 1 here and use it as u, and then the rest, x times e raised to x dx is dv. Okay. So again, only 1 out of the 4 ways, only 1 is the correct way of applying integration by parts. And how do we know which one is the correct way? We have some guidelines, specifically two independent na guidelines. Okay, so you can either choose one or choose the other. Okay, so yeah, in choosing which part of the integrand is u and dv, you have two options. The first option is to choose dv first, and then the rest of the remaining expression is u. Okay, or second option is to choose u first, identify or specify which part of the integrand is u, and then the remaining will be dv. Okay, if you opt for choosing dv or specifying dv first, then you have to look for the more complex, usually it's the more complex portion of the integrand. Okay, and while looking for the more complex portion of the integrand, you have to bear in mind that it has to be integrable. Okay, that's the main requirement for dv. It has to be integrable kasi we have to integrate man dv, diba? Okay, that's why it always involves dx, right? Or differential of any other variable, kasi it has to be integrated, or it has to undergo integration process. And then after specifying the portion for dv, the remaining factor or the remaining expression will be our u. Okay, or we can opt to choose or specify the portion of the integrand that we will be using for u first, and then the remaining for dv. If that's the case, then we have to look for, kasi u, if we want to specify kung anong portion ang u, then we have to look for the portion of the integrand whose derivative is a simpler function than the initial u itself. Okay, so if you already have chosen the portion of the integrand for u, then you check if its corresponding derivative is a much simpler function than the original expression for u. Okay, and then of course the remaining factors or expressions will be used for dv. Okay, so let's go back sa example. We have integral of x times e raised to x dx, diba? So in this case, we can follow the first guideline. Okay, kasi independent man ito sila, itong dalawa. Okay, we can opt to follow the first guideline or the second guideline, depende sa inyo. But in this case, it's very obvious naman na we have to let u be x, kasi if that's the case, if u is x, then its corresponding differential is just dx or 1, diba? 1 dx, which is a simpler na function or expression. Yung 1 is a simpler expression than x. Okay, and then the remaining na expression, which is e raised to x dx, that would be for dv. Okay? And then again, you have to check na the dv portion should be integrable. Okay? It has to be integrable kasi we need to integrate the dv portion. Okay? And in this case, we have e raised to x, which is easily integrable kasi we have a direct formula, diba, for e raised to x, which is just e raised to x, right? So in this case, if dv is equal to e raised to x dx, then v is just e raised to x. Okay? So in this case, we applied the integration process, diba, in indefinite integration. So actually dapat merong plus c kasi nag-apply tayo ng indefinite integration. We can exclude the constant of integration here because we're still not done yet with the whole integration process naman, diba? Later on, after we complete the process, we can then add the constant of integration. Okay? So after identifying u and dv, and then after differentiating u or taking the differential of u, and after taking the indefinite integral of or integrating it on dv, then we can now proceed to the working equation of integration by parts. So again, we have integral of u dv is equal to uv minus integral of v du. Okay, so first part of the formula is the product of u and v. So identify nyo lang u in this case is x, and v is e raised to x. So take the product of the two, right? So u in this case is x, v is e raised to x. That's why we have your product of x and e raised to x minus the integral of v. V in this case is what? E raised to x. So we have your e raised to x. And du is dx. So plug in dx. Okay? So the resulting integral after applying integration by parts is now a readily integrable na integral. Okay? So integral of e raised to x dx is just e raised to x. Diba? And then we can now add the constant of integration. Okay? So final answer. So before we solve some more problems, let's talk about a much more convenient na method of applying IBP. So this is using an order of priority, no? So we will be looking at a list of priority, and in this case we will be focusing on the U portion of IBP. Okay, so we have a list. Whichever comes first in this list will be prioritized, kumbaga. So whichever comes first will be chosen as the U portion. Okay, so we usually use this list, this order of priority, no? LIATE. The acronym is LIATE. L stands for logarithmic functions, no? I is for inverse trigonometric functions. A is for algebraic, and then 3 is for trigonometric. Lastly, E is for exponential. Okay, so let's take, for instance, the previous problem, integral of x times e raised to x dx. All right. We have a product of x is an algebraic expression, and then e raised to x is an exponential expression. So according to the list, we have here algebraic first before exponential. So we choose the algebraic portion, x, as u. Okay, and then the remaining expression, which is e raised to x dx, is the dv portion. Okay, so same process from our previous na solution, right? Just proceed with the differentiation for u, and then the integration for dv, and then apply the working equation for integration by parts. Integrate again kasi there will be another integral that will be generated, diba? And then integrate and then simplify. Find an answer. Okay. So let's solve some more problems. We have here product of the integrand is product of x and ln x. So from liate. Okay. So we have here algebraic, x is algebraic, an algebraic expression. And then, so that's x, right? ln x is a logarithmic expression. So from the list, we have here logarithmic before algebraic. So we prioritize the logarithmic expression. Okay. So we have to let u be ln x. It also makes sense, class, kasi ang ln x, if we, for example, if we let dv be ln x dx, this is not solvable kasi we do not have a direct integration formula for ln x, diba? So our only way to solve this one is to let u be ln x and differentiate ln x kasi differentiable naman ang ln x, diba? As opposed to making it your dv, hindi siya integrable. Okay? So, yep. Meaning, the list makes sense for this particular example, right? So we now have u, the rest should be dv. Okay? So the remaining expression is x. Then of course we should include dx, right? So let's go back. Let's go back to u. From u we take its differential. So differential of ln x, that would be dx divided by x, right? And then dv equals x dx. V now is equal to 1/2 x squared, or x squared over 2. Okay. So this is now the resulting expression. This is from, again, this is from u v minus integral of v du, right? U is what? U is ln x. Okay. And then v is x squared over 2, right? So x squared over 2 ang v. Minus integral of v, again, v is x squared over 2. And then du is dx over x. Okay? So itong second term, itong integral na term, just simplify. So x squared over 2 divided by x. So this will result to, we can factor out 1/2, right? So x squared divided by x, that would be x. And of course times dx. So this is now integrable. Just integrate using power rule. So that would be x squared divided by 2 times 1/2. So overall that would be 1/4 x squared. Okay, talking about the second term. And then of course plus c. Okay. Next problem. So we have here integral of x sine x dx. Okay. So let's write down the list first. Liate. Okay. So what do we have here? X is it's an algebraic expression, right? Sine x is a trigonometric expression. So algebraic over trigonometric, then we should choose the algebraic portion for u. Okay, so let u be x, and then the remaining expression for dv, which is sine x dx, right? So from u equals x, take its differential. This will result to dx. And then dv, we have to integrate this portion. So v now is equal to negative cosine x. Okay. Then plug in the equivalent expressions to the working equation of IBP, UV minus integral VDU, right? So this will now be the resulting expression. Okay, so again, x is the u portion, right? From here. Then negative cos x is the v portion from dv, right? Minus integral of v, again, itong negative cos x is the v portion from here. And then dx is du, right? So uv minus integral of v du. Okay. And then the second term, the integral term, we can still simplify this one, factor out -1, right? And then proceed with the integration. Itong cosine x naman is readily integrable. We have a direct formula for cosine, di ba? Its antiderivative is positive sine. And then, of course, don't forget the constant of integration. Okay? Alright, so let's solve some more examples, particularly involving single integrands, meaning just one type of function. For example, given is inverse trigonometric lang ang integrand or logarithmic function lang ang integrand. Okay? And then we'll also deal with an integral where we can apply IBP more than once. So repeated IBP. Okay? And then we'll also encounter an integral for which we can apply IBP. Pero after applying IBP, there will be the integral that will be generated after applying IBP is the same as the initial or the original na integral. So kumbaga, it will go back to the original integral. That's why it's called cyclic IBP. Okay? So we'll talk about how to solve those kinds of integrals. And then, of course, exceptions to liate kasi nga, di ba, I mentioned earlier that the liate na method, it's not a 100%. It does not work 100% of the time. Okay, so there are exceptions. It has its own limitations. So may mga exceptions, okay? And the tabular method, it's also called the DI method, okay? I'm sure you're familiar with the DI method. It's a shorter version, but it's not entirely a shortcut, no? It's a shorter version kasi we'll just transfer, kumbaga, the terms in a table, and using the table, we can clearly see kung ano ang terms na dapat i-differentiate, kung anong terms ang dapat i-integrate. And then, kumbaga, mas organized siya if naka-tabular method or DI method. Okay? Sige, first one type of function ang integrand. Alright. We have your integral of arctangent of x dx. Okay? So, from liate, we only have one type, di ba? So, from liate, logarithmic, inverse trigonometric. So, inverse trigonometric. Second siya from the list, kaso wala namang other type of function. Okay? And in this case, we do not have a direct formula for arctangent, so we cannot use arctangent, or we cannot use dv for arctangent. Okay? Kasi we cannot immediately integrate itong arctangent. It's not integrable. We do not have a direct formula for arctangent na integral. Okay? So our only way for this to be solved is to let u be arctangent of x. So in this way, we can differentiate arctangent. Diba? We have a differentiation formula for arctangent naman. Okay? And then the remaining expression is just dx. So we let dv be dx. Okay? And then from u equals arctangent of x, du is dx divided by x squared plus 1. And then from dv equals dx, v is just equal to x. Okay, and then plug in so working equation, which is u times v minus integral of v du. So u times v, u is arctangent of x, and then v is x, right? So that's uv minus integral of v, again v is x, so v is x, and then du. Okay, du in this case is dx divided by x squared plus 1, right? So let's just rewrite the whole expression. Okay, so x arctangent of x minus integral of x divided by x squared plus 1 dx. Okay, and then the resulting integral, this one, the second term, right, is actually it's readily integrable no, using u sub and integration resulting to ln function. Kasi if we let u be x squared plus 1, the expression here in the denominator, the corresponding du is 2x dx, right? So we multiply 2 and then multiply 1/2. Okay, so we now have du in the numerator, 2x dx, and then u in the denominator, which is x squared plus 1. So this is integrable using the ln formula. Okay, so all in all, we have x arctangent of x minus 1/2 ln of x squared plus 1 plus c. Okay, so next, repeated application of IBP. So application of IBP more than once. All right. So this will be applicable if the resulting integral is still integrable using IBP. Okay, so we are allowed to use IBP more than once. All right, so we have here an integral of x squared cosine x dx. So let's refer to Leate for this one. We have your product ng algebraic, x squared is algebraic, cosine x is trigonometric. So algebraic over trigonometric, we have to let u be the algebraic portion, so x squared, and then dv is the remaining expression, cosine x dx. Okay, then from u equals x squared, du is what? 2x dx, and then v here is so integral of cosine x dx, that would be positive sine x. Okay, so uv minus integral of v du. All right, u is x squared, v is positive sine x, minus integral of v, again v is sine x, and then du is 2x dx. Right, so on the second term we can factor out 2. Okay, and then if you look at the integrand of the second term, x sine x, we still have a product of two different types of functions, diba? Algebraic and trigonometric pa din. Okay, so we can still apply integration by parts. So for the second time, let u be still the algebraic portion, which is x in this case, and then dv is the trigonometric portion, so sine x dx. Okay, so from here du is what? Dx, and then v is, so integral of sine x dx, that would be negative cosine x, right? So another uv minus integral of v du. So this is u from the second application of IBP, right? U is x, and then negative cos x is v. So this is uv minus integral of v, again negative cos x is v, right? And then this one is integral of v du. Du is dx. Okay. So we can simplify by distributing -2. Or we can do that later on, right? So here we have on the last term, we have negative integral of negative cosine x dx. So we can simplify this one by factoring out or distributing negative 1. So this will result to positive integral of cosine x dx. And antiderivative of cosine x is what? Positive sine x. Okay. So all in all, we have x squared sine x minus 2 times the quantity of negative x cosine x plus sine x plus the constant of integration. Okay. Or again, we can distribute -2. Okay. Now, when we apply IBP for the second time or for the third time, we have to be careful not to mix up U and dV. Okay. So for example, if we initially let U be the algebraic portion, then on the succeeding applications of IBP, we have to be consistent with U. So if initially it's the algebraic portion, then the second application U should still be the algebraic portion. And then if there's a third application, then it should still be the algebraic portion. Okay? So dapat consistent. Algebraic ang U, then algebraic all the way. Okay? Kung trigonometric ang dV na portion, then it should be trigonometric all the way. Okay? So be careful. For example, let's use the previous na example. So still x squared cosine x dx. And then after the first application of IBP, so from the first application, di ba, we let U be the algebraic portion x squared. So that would be du is 2x dx. Okay. So again, this is the first application ng IBP. And then dv is cos x dx, for which ang v is positive sine of x. Okay. So u times v, so x squared sine x minus integral of v is sine x, and then du 2x dx. All right. So now, what if we interchange the substitutions? Okay. So instead of u being the algebraic portion, let's try if we simplify ito, factor out 2, maging -2 integral of x sine x dx. So again, still have algebraic portion and trigonometric. Okay, so for the sake of discussion, let's try to change the substitutions, no? So instead of u be the algebraic portion, let's use sine x, the trigonometric portion, and then dv is ang algebraic, so x dx. All right. So now from u equals sine x, du is positive cos x dx. All right. And then from dv equals x dx, take its indefinite integral or its antiderivative. That would be x squared over 2. Okay. Then plug in. Ayan. So again, uv minus v du, right? So u in this case is sine x. We have sine x times v. V is x squared over 2 minus integral of v du. Again, v itong x squared over 2. And then du is cosine x dx. All right. So from here we can distribute -2, and let's see what happens. So negative 2 times x squared over 2 mag-cancel out on 2. We have negative x squared sine x. And if you look at the first term, they are equal, but opposite signs. Equal magnitude, opposite signs. So cancel out, right? And then negative 2 times negative integral of x squared over 2 cosine x dx. So again, mag-cancel out on 2. Then negative mag-result to positive. Okay? Therefore, ang maiwan is the original integral. Therefore, na-neutralize ang application natin. The first time we applied IBP, na-neutralize siya because we interchanged the u and the dv portions. Okay? So be careful. After this one, balik lang sa original integral. And walang naiwang other terms. Tapos if we transpose itong, if we try to transpose itong integral of x squared cosine x dx to the other side, so maging integral of x squared cosine x dx minus integral of x squared cosine x dx, then that would be 0. Okay? So, kumbaga, wala. We did not solve the problem. We did not arrive with the antiderivative. Okay? So, nagbalik siya sa original na integral. Okay? So, again, be consistent. If initially the u portion ng integral is the algebraic portion, then it should be algebraic portion all the way. Right? If it's trigonometric, then trigonometric all the way. If it's exponential, then exponential all the way. Okay? So, be consistent. Okay? So, let's see cyclic IBP. So, usually it will occur if exponential and trigonometric like this one. Okay, so let's see. E raised to x sine x. Let's see if we can use liate. Okay, so we have here exponential and trigonometric. So trigonometric over exponential. Let's follow liate. So let u be the trigonometric portion, so sine x. Alright, and then the remaining for dv, e raised to x dx. Now, if we follow the original guidelines, no, like yung sa first two na guidelines na choosing dv first and then the remaining is u, or choosing u first and then the remaining is dv. For the second, yung choosing u first, kasi diba we have to choose the portion of the integrand for which its derivative is simpler than its original na expression, no? So in this case, it does not actually work that way kasi pag if we let u be equal to sine x, its derivative is cosine x, which is the same degree, is the same level of complexity, kumbaga, if you will, sa original, no, na sine x. Ang cosine x is the same lang man siya na level, trigonometric function pa rin naman. Okay? Now, if we, for example, if we let u be e raised to x, its corresponding du is still e raised to x, no? So, same level din. Alright? For this particular example, we can actually do this either way. So, we can let u be e raised to x, or in this case, we can let u be sine x. Kasi, same naman ang result. Same lang naman ang result. Okay? So, you can try on your own. You let u be e raised to x dx. Okay? Kasi nga, the resulting differential for both sine x and e raised to x is the same degree lang, kumbaga, same level of difficulty or complexity, if you will. Okay? So, regardless of whichever you choose, we'll arrive at the same answer. Okay? So, let's work on this example using these substitutions. So, u equals sine x. the corresponding du is cosine x dx. Okay, and then from dv equals e raised to x dx, v is just e raised to x. Okay, so plug in to the working equation. Okay, u times v, u in this case is sine x, and then v is e raised to x. Okay, minus v, again v is e raised to x, and then du is cosine x dx. All right, so let's just rewrite this: e raised to x sine x minus integral of e raised to x cosine x dx. The resulting integral, all right, itong second term is still integrable using Ibp kasi we still have product of two different functions, exponential and trigonometric. Okay, so again, be consistent kasi we are, in this case, we are applying a second round of Ibp. So still, u portion is the trigonometric portion. So cosine x, and then dv is still the exponential portion. Okay. So from here, du is what? Negative sine x dx, and v is still e raised to x. Okay, so plug in. All right, u times v, u in this case is cosine x, right? V is still e raised to x minus integral of v, v again is e raised to x, and then du is negative sine x dx. Okay, so let me just rewrite this one. Okay, so all in all, we have e raised to x sine x minus e raised to x cosine x minus integral of e raised to x sine x dx. And if you look at this integral of e raised to x sine x dx, it's the same as the original integral. Okay. However, unlike the previous example, di ba, first two terms of the resulting na antiderivative ay nag-cancel out. Pero in this case, hindi mag-cancel out. So, no problem for this one. And then for the last term, integral of e raised to x sine x dx, we can actually transpose this one to the left-hand side of the equation. Okay? Kasi ang left-hand side of the equation, it's always ito, di ba? Kasi this is our original na integral. And this one, the left-hand side of the equation is equal to, of course, whatever is in the right-hand side of the equation. Okay, so we can transpose itong negative integral of e raised to x sine x dx to the left-hand side of the equation. Okay, so it will become on the left-hand side of the equation after we transpose, actually, before we express this as 2 integral. So let me just show you kung ano nangyari. Okay, so lagay ko na lang sa baba, plus left-hand side of the equation, initially or originally, we only have integral of e raised to x, diba? Sine x dx. Okay, and then if we transpose this term, negative integral of e raised to x sine x dx, it will become positive integral of e raised to x e raised to x sine x dx, right? This is on the left-hand side of the equation. Okay, that's why it became 2 integral of e raised to x sine x dx. Okay, and then because we are only asked to or required to find the integral of e raised to x sine x dx, then we have to isolate only this portion of the integral. Okay, so dapat ito lang. We have 2 now, so what do? We divide both sides by 2. Therefore, all in all, integral of e raised to x sine x dx is equal to what? 1/2 e raised to x sine x minus e raised to x cos x. Okay, and of course constant of integration. All right, so let's talk about the exceptions to liate. We actually have an example, no, where liate is not applicable. Yung arctangent lang ang yung one type of function lang ang integrand. Okay, kasi wala namang dalawang function na i-compare from using the order of priority sa liate, di ba? That's one exception. Okay, so for example, another example, no, one type of function. So we have here it's just a trigonometric function ang integrand. Okay, so we do not have another type of function that we can compare with secant cube x in this case, so that we can identify which comes first in liate na list. Tama ba? So this is an exception to liate. So what do? We can use trial and error for this one, pero pinaka-applicable is to break secant cube x into two parts. Kasi nga, we are applying IBP, di ba? We have to break the integral into two parts. One for u na portion, the other is for dv portion. Okay? So in this one, in this case, we can break secant cube x into product of secant x and secant squared x. Okay? So here, the best way possible is to let u be secant x, and then dv is the remaining expression, secant squared x dx, right? So u equals secant x, differential is secant x tangent x dx, all right? And then from dv equals secant squared x dx, this is integrable. We have a direct formula for secant squared x, diba? Its antiderivative is tangent x. Okay, and then we plug in to the working equation of IBP. So u times v, u in this case is secant x, tangent x is v, diba? uv, minus integral of v, v again is tangent x, and then du is secant x tangent x dx. Okay, so let's just rewrite the integral term. Okay, we have integral of secant x tangent squared x dx. So if you look at this integral, it's not readily integrable in this form, so our option is to apply identity, no? So if you recall from trigonometric integrals, this expression here, tangent squared x, can be converted to secant using trigonometric identity, and let's see what happens. Okay, so let's use the identity. So secant squared x minus 1, and then expand or distribute secant x. So we now have secant cube x and then negative secant x. Secant x is readily integrable, right? We have a direct formula for secant x. However, we have integral of secant cube x. So let me just rewrite this one. Okay, to just distribute the integral operators and negative 1. So negative integral of secant cube x dx, then negative times negative, so positive integral of secant x dx. So again, itong last term, this is integrable, right? We have a readily available na integration formula for secant x. And then, looking at the second term, integral of secant cube x dx, this is the same as the original integral. Pero, similar magnitude, but different signs, opposite signs. Okay? So, if we try to transpose this one, hindi sila mag-cancel out. So, wala problema. So if we transpose negative integral of secant cube x dx to the left-hand side of the equation, it becomes 2. The left-hand side of the equation becomes 2 integral of secant cube x dx. Okay, and then we divide both sides by 2. Right? And then integral of secant x dx, antiderivative ng secant x is ln secant x plus tangent x. Okay? And then again, left-hand side of the equation becomes 2 integral of secant cube x dx. And we are only required to find integral of secant cube x dx. So we have to isolate integral of secant cube x dx. Alright? And we do that by dividing both sides by 2. Okay? So, final answer. Alright, so another example which demonstrates the limitation of the Liate method. Okay. Oops. So we have your integral of x times e raised to x all over the quantity x plus 1 squared. Okay, so this cannot be solved. This is not solvable by just simply separating the integral into the algebraic portion and the exponential portion, and then applying the Liate method. Okay, so pinaka-applicable for this one is to let u be x times e raised to x, alright? And then the remaining expression will be for dv. Okay, so we are left with what? Dx divided by x plus 1 squared. Okay, which is integrable naman, diba? Using just u sub and power rule. Okay, so no problem. And then let's go back sa u. U is x ex. I mean x times e raised to x. So let's take its differential. All right. So we have two different types. So product rule, copy x and then differentiate e raised to x with respect to x. So that would be e raised to x plus copy e raised to x and then differentiate x with respect to x. That would be 1. Okay. So this is now x times e raised to x plus e raised to x dx. Okay. And then dv equals dx divided by x plus 1 squared. So let u be x plus 1. Du is just dx. And then we can rewrite this as an exponential with negative exponent. So we can transfer x plus 1 raised to 2 to the numerator so that we can easily see that it takes the form u raised to n du. Okay, and the corresponding antiderivative is what? Negative 1 over x plus 1. Okay, and then we plug this in. We plug in the equivalent expressions to the working equation for IBP. Okay, so ito class naka ano lang, the integrand or the integral is separated into two parts. So x times e raised to x and itong dx divided by x plus 1 squared. And then apply IBP. Yan. This is u, right? This is v. This one minus v again times du. So this is actually du. From here we can factor out e raised to x. Okay, so that we'll get e raised to x quantity x plus 1 dx. Alright, so that's what happened here. E raised to x plus 1 dx. Alright, so from here, let's simplify. So first term, all in all, we have negative x e raised to x over x plus 1 plus integral of e raised to x dx na lang kasi mag-cancel out ang x plus 1. Okay, and then negative naging positive. right? Then integral of e raised to x dx, very much integrable. That's just e raised to x. And then, of course, constant of integration. Or we can simplify this one. We can actually simplify this further by taking the LCD of the first two terms. So LCD is x plus 1, right? So let me just isolate the first two terms. LCD is x plus 1. So first term, numerator of first term is negative x e raised to x. Okay. Then we have here plus e raised to x times x plus 1. So that would be what? E raised to x times x. So e raised to x times x. And then e raised to x times 1. So plus e raised to x. Okay. So first two terms will cancel out. Remaining is e raised to x over x plus 1. Alright? And then plus c. Okay. And then lastly, we'll discuss the tabular method, or also known as the DI method. Why DI we'll see later on. Okay. So this is a shorter version but not entirely a shortcut of IBP kasi it's just it's still based on the proper na IBP, pero it's made shorter because we can transfer the terms in a table. Okay, so mas organized siya. We can clearly see the terms that need to be differentiated and the terms that need to be integrated. Okay, so we have a differential column and an integral column. That's why it's DI, differential and integral. Okay. All right, so let's try to solve the previous problem, integral of x squared. Integral of x squared cosine x dx, where u is x squared and dv is cosine x dx. So we already established that u is x squared from the liate na list. Okay, so we'll still use liate for this one. But instead of writing everything in terms of properly in terms of an expression, kumbaga, we'll transfer everything in a table. Okay, so we have first column, the sign of the terms, and then second column is the differential na column. So these are the terms that we need to differentiate. Okay, and this is based on the u portion. Okay, and then the integral portion, which is based on or corresponds to the dv portion, kasi we have to integrate these terms under the I column. Okay, so sa science class, we just need to list down alternating na positive, negative, positive, negative, so on and so forth. Basta alternating, positive, negative, positive, negative. Okay, and then D, this is the, again, this corresponds to the U portion, okay, of from the liate na method, no? Or use, if you opt to use the two general methods, basically U is x squared using those methods. Okay, so we put x squared here, and then the integral column corresponds to the dv portion. So in this case, cosine x. All right. And then what do we do next? Let's focus on the d column, kasi from here we have to differentiate. Okay, starting from x squared. So differentiate, that would be 2x. Differentiate again, that would be 2. And then differentiate again with respect to x, that would be 0. Okay, So we stop if the derivative is 0, right? And then from the integral column, starting from cosine x, we integrate, or we take its antiderivative. So antiderivative of cosine x, that would be what? Positive sine x. Okay. And then antiderivative of sine x is negative cosine x. Alright? And then antiderivative of cosine x is positive sine. And since we have negative here, so that would be negative sine x. Yes. So we stop here because its corresponding counterpart in its row is already 0. So we stop here. Okay. Then, so the integral initially requires us to, or the problem requires us to find integral of, so let me just write here, integral of x squared cosine x dx. Okay. So the resulting antiderivative is the product of the diagonal entries. Okay. Starting from the positive sign. So you go to the right side horizontally, and then we go from the D column going to the I column diagonally. So we skip one row for this one. Okay. So first term is positive x squared sine x. Okay. Then again, we do the same process, starting from negative sign this time. So negative 2x times negative cosine x. So that would be what? Positive 2x cosine x. Okay. And then positive 2 times negative sine x. So that would be negative 2 sine x. Okay. And then this will be the last term, because if we try to multiply negative 1 times 0, product is still 0. So we stop here, and then we add a constant of integration. Okay. So this is tabular method. This is one type of tabular method. This is if the derivative goes all the way to 0. Okay. If we reduce the differential column, the derivative column to 0, then that's the first type of, that's the first case for a tabular method. Okay, so we have another case. So we have two more cases for the tabular method or the DI method. Okay, so for example, let's check this one pala, no? If this results to, if this is the same as the previous na answer natin using the proper na application of IBP, kumbaga. Okay, so let's see. That was problem number, ayan. Ayan. So x squared cosine x dx, its antiderivative is x squared sine x plus 2x cos x minus 2 sine x plus c. So let's see if parehas. So again, x squared sine x ang first term, 2x cos x ang second, tapos negative 2 sine x ang third. So x squared sine x plus 2x cos x, and then minus 2 sine x. So parehas. X squared sine x plus 2x cos x minus 2 sine x. Okay? So same. So another case for the tabular method, kasi diba, the number one is if the derivative term goes all the way down to 0. There are cases kasi na hindi mag-0, diba? Especially if ang u na portion is not an algebraic na expression. Okay? So algebraic lang ang mag-result to 0 if we differentiate again and again, no? So let's see if, for example, algebraic and let's try algebraic and logarithmic. Okay? Kasi in this case, ang U portion is not the algebraic portion. Therefore, the corresponding na D column does not start with algebraic, but instead of algebraic, we'll start with logarithmic. Okay, so let's try for this one. Let's try the DI method. Okay, so sines derivative term or the differential term and then integral term. Okay, so sines again plus minus. Okay, and then here we base the expression for the D column on the U portion. Okay, so that would be what? ln x. Then the integral column starts with x. Okay, all right. So let's take the derivative of ln x. That would be 1 over x. Okay, and then if we differentiate 1 over x, it will give us another algebraic function, and it does not end with 0. Okay, so from here we can stop for now. Okay, and then we proceed with the integral column. Okay, so we started with x. We have x to start with. We take its integral, so that would be 1/2 x squared, or x squared over 2. Okay, so to stop or to determine where to stop for this type of integral where we cannot, or it does not end with 0 ang differential or derivative na column, we look at the last row. Okay, if the last row, the product of the last row is integrable already, then we can stop the DI method. Okay, so if you look at 1 over x and x squared over 2, its product is already integrable na, di ba? So we can stop here. We can write now the resulting na antiderivative. So integral of x ln x dx is now equal to what? So positive ln x times x squared over 2. So that would be x squared over 2 ln x. Okay, so same with this one. However, we now have we copy the last row, but it's still an integral. It's still an integral na wala pa na evaluate. So we just copied this last row. So minus integral of product ng 1 over x and x squared over 2. Okay, so that would be 1/2 x squared over 2, x squared divided by x, so that would be x, right? And then of course we put dx kasi we still have to integrate. Okay, and that would be x squared over 2 ln x minus, so this is x squared over 2 times 1/2, therefore 1/4 x squared plus c. So same lang. Alright, so another way to apply DI method is if pag cyclic na IBP. Okay, so let's see. Cyclic na IBP yung e raised to x. Ito e raised to x. Sige, sulat natin dito. E raised to x sin x dx is the problem. Okay, and let's try to use the tabular or DI method, and let's see if we'll get the same answer. So e raised to x sin x. dx. Okay, so let's start with the table, no? Sine d column I column. Okay, so plus minus, and then using the proper way of applying IBP, di ba, we already established that ang u portion is ang sine x. So we can do that. We can still apply this one. So d again corresponds to the u portion. So you can put here sine x. Tapos yung integral na portion is ang e raised to x. Okay? So differentiate starting from sine x. That would be positive cosine x, right? And then differentiate again. So that would be negative sine x, right? Now, if we differentiate further, this will just be, so this will give us another trigonometric function, and then differentiate again another trigonometric function. So it, kumbaga, paulit-ulit lang sine x, cosine x, sine x, cosine x. So it will not stop. It will, the same with the previous na example, it will not go all the way to 0 ang ihang derivative. So we can stop for now, and let's see later on what will happen. Okay, so if we proceed to the integral column, so we have e raised to x, take its integral, that's e raised to x pa din, e raised to x, and then e raised to x, so on and so forth. So when do we stop the DI method for this type of integral? Now, again, we look at a certain row, no? So if from the previous na example, our determining factor is if the last row is integrable na, then we stop, no? Pero it's not the same case for this one. Kasi ang resulting na last row, if we further differentiate and integrate, is still not readily integrable kasi product of exponential, product of trigonometric. Pero for this kind of integral, we stop if mag-repeat ang original na integral. Okay, kasi nga ito ay it's an example of a cyclic IBP. So if you can see na after a few rounds of taking the derivative and taking the integral, if you can see na nag-repeat na nag-result na siya to the same na integral from what was initially given. Like in this case, meron tayong e raised to x and sine x. So product nito is the same as the original na integral, right? And if that's the case, then we stop the differentiation and the integration process. Okay? And then we can now write the partial antiderivative. Okay? So from integral of e raised to x sine x dx, we now have, so still the same method. So from positive going horizontally to the right side. So positive sine times e raised to x. So e raised to x sine of x. Okay? And then we have here minus cosine x times e raised to x. Okay? So that would be e raised to x cosine x. Okay? And then plus negative sine x. So this will become negative, no? And then some partner, so we integrate again itong e raised to x so that we can generate a partner for sine x, right? So positive, negative, this is negative or minus sine x times e raised to x. So e raised to x sine x. Pero basically, class, we actually have to copy lang. Kasi we stopped at this row naman, di ba? We just have to copy whatever is on the last row and take its integral. Okay? So integral of positive times negative sine x. So minus integral of e raised to x times yung sine x. Okay? Ayan. And then since we now have the same integral, of course we need to put dx kasi we still have to integrate this portion. Okay, so this is e raised to x sine x dx, the same with the original integral. Okay, so we can combine this with the original integral, transpose this one. So initially this is negative on the right hand side of the equation. If we transpose this to the left hand side of the equation, it becomes positive. Okay, so we now have integral of e raised to x sine x dx plus integral of e raised to x sine x dx. So it becomes 2 integral of e raised to x sine x dx on the left hand side of the equation. This is equal to e raised to x sine x minus e raised to x cos x. Okay, and then divide both sides by 2, and of course we have the constant of integration. Okay, so all in all, integral of e raised to x sine x dx is equal to 1/2 e raised to x sine x minus e raised to x cos x plus c. Okay, so same with what we obtained earlier using the proper application of IBP, right? So 1/2 e raised to x sine x minus e raised to x cos x plus c, the same. Okay, so that's how we apply the DI method. Number 1, first case is if the derivative column can be reduced to 0 after a few rounds of differentiation. Okay, that's the first case. Second case, if it does not reduce to 0, then we base on the last row. If the last row is already integrable, then we stop the differentiation and the integration using the DI method. And then the last case, this one, if the last row contains the same expressions as the original integral, then we stop the differentiation and integration in the DI method. Okay, so that's how we apply the DI method.